Hi everyone. As you recognize or may recognize or remember from the introductory video, we were going to begin this week talking about disassembly, meaning the ability to statically, engage with malware by disassembling it. But prior to disassembling it, let's talk about assembly, as specifically assembly language. So if you've ever wondered how your computer actually understands your source code, now we've all programmed in Python, Java, C Sharp, C++. So we all know the concept, if you will, of actual source code. Now with source code, it is about as close as the English language as you possibly can get. And, the whole purpose of different languages, like the difference between Perl and Python, some languages just happen to be closer to English language than others. Some people say that, for example, Python is probably as close to pseudocode, as you can possibly get. But the point is that, between whether or not you use a harder to understand language such as Perl or, C++ or C, or an easier language such as Python, they all start with human readable source code. But that's not what your PC understands. It understands those zeros and ones. So what is assembly language? Assembly language is basically it kind of rests right up above the actual pieces of hardware, because at the end of the day, when you write language or when you write programs, you're actually programming. You're programming the actual, I'm going to say, components of your PC, such as your hard drive, your disk drive, and things like that. So let's take a look at what assembly is. It's a low-level programming language that acts as a connection between the code that we write, the source code, the things that we may type in an IDE, such as Java's IntelliJ or NetBeans or what have you, or Visual Studio, or Visual Studio Code, whatever we're typing in Visual Studio Code or whatever IDE we want. How does that interact with your computer's hardware? Well, somehow, some way, that information gets transferred into zeros and ones. So what is assembly? Assembly is the lowest level programming language that acts as a connection between the source code and machine code. When I say machine code, basically machine code are those zeros and ones. Okay? Unlike Python or Java, which are designed for humans to read and write them, assembly language is much closer to the computer's hardware. It gives, so if you know assembly, you can literally control the CPU, the memory, and it allows you to optimize how your computer acts. So things like each instruction in the assembly language tells the computer to perform a very specific operation, such as moving data between registers, performing arithmetic, or jumping to a new instruction. Okay, so let's take a look at the basic components of assembly. Now, the basic components of the assembly language are essentially the building blocks or basic components that allow you to communicate directly with the computer's hardware. And the assembly language uses things like instructions, which tell the computer exactly what to do, like whether or not to add two things. And it also uses operands as action, so adding, subtraction, okay? And it uses mnemonics too, which are human readable abbreviations. Now, registers right here are nothing more than little storage facilities, because when you tell assembly language to do an instruction to do something, that instruction has to rest on somebody. on somewhere. So think of a register as like a mini high-speed hard drive or piece of storage of which that instruction lives on. So let's take a look at CPU registers. CPU registers are, as I said, look, think of like the register is like this little container right here. It's holding these instructions. Okay, so let's say, for example, we took a look at the different kinds of registers or different kinds of different types. So each register, each type of register serves a specific purpose. Now, a general purpose register can hold data for different operations. Special purpose registers, okay, are holding the current instructions being executed and the program counter keeping track of the address of the next instruction. And these status registers contain information about the current state of the CPU, including flags for arithmetic operations. Let's take a look at flags in assembly. Now, flags are special bits. Now, if we can think of a flag as a bit. Okay, so like the smallest flag, the smallest bit is 1 bit. So, for example, you might have 0 or 1 to indicate whether or not it is off or on. That's an example of a flag that might be in a TCP IP packet. When it comes to assembly language, there are special flags that are ticked on or off. Examples are 0 flag. That is set when the result of an operation is 0. The carry flag is set if the operation or if the arithmetic operation produces a result for too large for the register to hold. And that's easy to do because assembly languages are meant for small pieces of data. Let's take a look at the overflow flag. That tracks whether an arithmetic operation results in an overflow. Obviously, it's similar to carry flag. The carry flag will carry that overflow and will communicate with the overall flag. The sign flag indicates whether the result is negative or positive. Here is and there's other flags as well, not mentioned here because this is supposed to be just an introductory type video. So when it comes to memory and addressing modes, memory refers to the physical locations where the data is kept, allowing programs to retrieve and manipulate information. Okay, now addressing nodes, okay, they define different ways we can access the memory. For common addressing modes include immediate addressing, direct addressing, and indirect addressing. For example, in immediate addressing, you might use an instruction like add R1 to 5, which adds the value of 5 directly to the register R1. Now, when I say register R1, that means that there is a memory location, okay, where R1 is. So think of R1 as a variable. So whatever the variable is R1, whatever that memory location has, okay, it's going to add that to 5. So it's essentially adding 5 to a memory location. For those of you that studied C++, you recall the concept of pointers. Now, pointers, okay, are there to move bigger pieces of data, okay, and pointers. So in other words, what C++ allows you to do is to not necessarily reference an actual variable value of, let's say, 5. Okay, it allows you to reference the memory location of a variable because that is for speed. Speed is a concern for applications as you get as the values get larger and larger. So to take two variables like and add them together, it's fine if one variable is 5 and the other variable is 4. That is simple. But imagine, if you will, the variable is 5,321,531. That can get pretty memory and processor intensive. So what C++ does with pointers, they will manipulate not the variable of that 500 million value. They will manipulate the place in memory. Okay, so that saves on that does save on time. Basic assembly instructions. They fall into several categories, each serving a unique function in programming. Arithmetic instructions perform mathematical operations. For example, adding R1 and R2 adds the value in register R to the value in register 1. Okay, and the same thing with subtracting. And then we have the logic, and then we have control. Okay, let's take a look at how assembly is executed. So assembly language is executed through the fetch, decode, execute cycle. Let's take a look at each one. For example, during the fetch phase, the CPU retrieves an instruction from memory, typically pointed to by the program counter. Okay. Now in the decode phase, the CPU interprets the fetched instruction, determining what action is required and identifying the involved operands. Okay, now operand is the items that of which you're performing action on. An operator is something where you are actually manipulating the operands in a certain manner. Finally, in the execution phase, right here, the CPU carries out the operation as specified by the instruction. Let's take a look at a practical example. In this assembly code example, we start by loading the values 5 and 10 into the registers. Okay, so move R1 with 5. We move 10 into R2. And the add instruction combines these two values and stores the result in R3. So to determine whether or not the result is even or odd, we perform the bitwise AND operation right here, and that effectively checks the least significant of the sum. If it's 0, the number is even. If it's 1, the number is odd. Let's take a look at the real world applications. Okay. Assembly language may seem low level compared to modern programming language, but it plays a vital role in many real-world applications where performance and precise control of the hardware is crucial. For example, it is commonly used in embedded systems like those found in cars, medical devices, and household appliances, where efficiency and direct control over hardware resources are essential. Also, game consoles and graphics programming also utilize assembly for optimizing performance and making the most out of hardware capabilities. Additionally, assembly is critical in device drivers, which act as the interface between hardware and operating systems. Even parts of the operating systems themselves, especially those that need to interact directly with hardware, are often written in assembly. By using assembly languages, developers can fine-tune programs to run as efficiently as possible, which particularly makes important which are particularly important in resource-constrained environments or performance-critical tasks. Okay, we're almost done, thankfully. What are the limitations of assembly? While assembly languages offer significant advantages in terms of performance and control over hardware, it comes with notable limitations. One major drawback is its complexity and verbosity. Writing code in assembly requires a deep understanding of the underlying hardware architecture, which can be daunting. This complexity leads to longer development times, as even simple tasks can require extensive lines of code compared to high-level languages. Additionally, assembly is not portable. Code written for one architecture typically cannot run on another without significant modifications. The lack of portability makes assembly less suitable for large-scale software development, where flexibility and maintainability are essential. Furthermore, assembly lacks the rich libraries and built-in features available in high-level languages, limiting its use in modern software applications. Overall, assembly is powerful for specific tasks. Its limitations can hinder productivity and adaptability in the fast-paced modern world of software development. Now, in conclusion, assembly language serves a crucial role and a crucial tool for programmers who need precise control over hardware and require optimal performance in their applications. While it offers significant advantages such as speed and direct connection with the CPU, it also presents challenges like complexity, lack of portability, and reduced flexibility for large-scale software development. Understanding that aspects helps developers make informed decisions about when and how to utilize assembly, ensuring they leverage its strengths while being mindful of its limitations. And that's about it for this micro video. This is all about assembly as an introductory concept. And here's an example of a real-world piece of assembly. Now I'm going to go ahead and make this a little bit bigger. And this is my Debian run on my MacBook through virtual, VMware Fusion. And here I list out my directory right here. This is Ubuntu. And as you can see, there's nothing of interest here. So I make directory, and that's yesterday, January 17th, 2026. I then changed into that directory, and I did the vim firstprog.c command, and that creates the program, the empty program firstprog, because it's a brand new program. And then I type this in, okay, and obviously it's going to use a for loop to walk through the printing or puts in C language, hello world, and we're going to return 0. Now what happens is, I believe I had to install, I had to install GCC. I can't remember, but you just do apt install GCC. So GCC allows you to compile. It's a compiler for C programs. What I mean by compiling, you write the source code, you compile it, and then it becomes an executable. You have to run GCC to become, and you run the C program, and then you do -o. That allows you to specify the name of the executable. -o means out. What is the out format? And you specify, hey, if the C program is named firstprog, the executable should also be named firstprog. And then I did a ls of my new directory, of which there previously was nothing in it except firstprog.c. And then once I compiled it, it became an executable firstprog. Then I executed first prog with the dot / first prog, and then it actually executed it. Now I can use the object dump, okay, and I can take a look at what your machine at the assembly language of the first prog, and we can see the all the columns right here. Now 774 is the place in memory, okay, and this refers to the line. This refers to, my apologies, that refers to the line number, and this refers to the place in memory, and this refers to those mnemonic type commands. We have move right here. That should be easy to see. We have add, and then we have, looks like we have string right here. We have another move command right here, and then we have the values that it is actually moving right here. Okay, so the object dump allows us to get insight as to what the computer actually sees. Okay, so this is just an introduction into assembly.